Well, hi everybody. Welcome back to the hardest video ever made. This has been my toughest one to make. We've had sound issues and I've had problems making it, so we're going to give it another go today. Well, what is this about? This video is about the central limit theorem. And what I want to do is I want to illustrate what the central limit theorem is saying. Now, we're doing it in class with the penny problem. We're doing it here in tomorrow or another day in class. I'm going to show you the Rice University applet that shows what a sampling distribution is as well. And so there are a number of things I want you to get out of this video. The first one is really, how do you find a sampling distribution? And when they talk about it, what are they really talking about? So that when we start to do statistics that we're going to be able to make predictions on and so forth, you're going to see that how this information that we're doing right now, how the central limit theorem kind of underlies everything that we're doing. The second thing is I just want to show you the procedures, because we do means and standard deviations, etc. And it's really easy to get mixed up on which one is which and which one you're talking about. And what do we mean by all samples of the same size? And when we start to compare things, what should we notice? So, and those are the exact problems you have to do. You'll notice there are two find mean and standard deviation problems, both of which are quite easily done. There's listing all the samples, but that is not easily done, especially on number 9. Number 10 is quite a bit easier. That's why that one's assigned to you. And after you watch this video, I want you to make sure you do number 10 as far as you can and bring it to class tomorrow. And then we're going to talk about the comparison, which are really the results of the central limit theorem. Okay, so let's get started on this. I'm going to shrink this up and we're going to get started. So number 1, we want to find the mean and standard deviation. Well, for this small population, which are the number of movies watched by 4 family members in a month, that's fairly easy to do. The mean of the population is equal, in this case, it's so small I'm just going to do it by hand. 4 plus 2 plus 8 divided by 4, which of course is equal to 3.5 movies. We want to label whatever things mean. And then the standard deviation is going to equal to, essentially, if we did it by formula, since this is small, we could do that, or we could just do it by technology. And I choose to use technology, so I get approximately 2.96 movies. And that's using the population standard deviation. Okay, so our next task then is we need to list all the samples. And so when it comes to listing all the samples, that is actually the hardest task. And so just to help us out here, I want to give an example. They also say list the samples without replacement. The reason they say without replacement is because our population is so small, we need to guarantee the independence of the items that are in our samples. And what that means is we have to put an item back in and draw it back out. And so even though our samples won't be distinct from one another, they come in different orders. So in other words, order kind of matters here when you draw things out. So if you draw 0 out first, a 2 second and a 4 third, or a 2 first, a 0 second and a 4 third, those are actually 2 different samples in this case. And that's the key to the problem you're going to do. Let me write a few examples. For instance, I could write 0, 2, 4. I could write 0, 4, 2. I could write 2, 0, 4. I could write 2, 4, 0, etc. And all these are different samples of size 3. And so you want to draw them all out. So how many are there? So I need to think about this. Since I'm doing replacement, that's really a counting problem. And basically I get 4 on the first one, 4 on the second one, and 4 choices for the third one. And 4 times 4 times 4 is actually 64 total samples. All right, so that's a lot. And so I'm not going to show you all 64. I'm going to actually show you where I do it. I'm going to show you all 64 according to the textbook. The textbook has them all listed, and I'll show you where they are in just a moment. But when you do problem 10, you only have to draw out samples of size 2. So you're only going to have 4 times 4, or 16 possible samples. And so your options are going to be like 0, 2, 2, 0. So it's a much simpler set of options. And so I think you'll be able to list all 16 of those. So I hope what I've said now will help you to do what I think is the hardest part of this problem, and that is listing all the samples. So I'm going to paste a picture and pause this right now. You might want to try and pause and find your 16 samples on problem 10 and your mean and standard deviation. So if you do that right now, you'll have 16, and then I'll show you all 64 in just a moment. Now what you see before you is a picture of the answer for this problem in the back of the book, or part of the answer. And what needed to happen is you needed to list all possible samples that you could get with replacement. And as you can see, there was 0, 0, 0, 0, 0, 2, 0, 0, 4, 0, 0, 8, 0, 2, 0. Now notice 0, 0, 2 and 0, 2, 0 have the same elements, but because of with replacement, they're actually considered a different subset. And then along with that, over somewhere around here, you'll see a 2, 0, 0 right down here on the video. And so given those things on the video, that tells us that there were a lot of them, and they showed us all 64 of those possible subsets, and why there are 64. Now, the next thing you have to do, if you go back to the directions, is you have to find the mean and standard deviation of the sampling distribution. So what's the sampling distribution? And this is another purpose of this video, is to make sure you know what the sampling distribution is. All these samples that you see here, all these samples that are listed, okay, those are all samples of size 3 from the population, all right? What we did is we took each one of these samples. So this first one was 0 plus 0 plus 0. That's 0. I divided it by 3 and I got 0. The second one, 0 plus 0 plus 2, divided by 3 is 0.67. And so on. 2 plus 8 plus 2 is 12, divided by 3 is 4. And so forth. So I did this over and over and over for each sample. Well, what are these numbers in the second column by each of the elements in our sample space? So notice the 3 elements chosen, that's our sample. All of those give us our sample, 64 different items. You could call that a sample space. These then are the averages of all those samples, the averages. So they're sample means, if you wish. They are sample means, okay? And you can see there are lots of different sample means. So if you take all those sample means and put them together in a set, then that is the sampling distribution. The sampling distribution of means is the collection of the means of all samples of the same size. Okay? And so that set of these numbers is a sampling distribution. Now to find the mean, I got to add them all up and divide by 64. Or I could make a list, for instance, a frequency table where I call the mean X bar, and then the frequency is over here, so there is 1, 0. And then 0.67, I can see very quickly, there's a 0.67, there's a 0.67, there's a 0.67. So there may be a few of them all the way through. So I would put the mean as 0.67, and then I would write down the frequency. And I believe that's all of them, so there are 3. And then I would go to the next number, all right? And so the next number in this case is 1.33, so I'll write 1.33, and there's 1 of them, and 2 of them, and 3, and I don't see any very quickly on what I'm looking at there. So I just got to move it. Oh, here's a 1.33 down there, right here, and a 1.33 there, and one here. And so I believe that is all of them, the 1.33s. I don't see any others, so I would say there would be 6 of those. So what I want you to do is I want you to go through this table. It's in your answer key in the back of your book. My book is a little different because it's teacher edition, but it was in the section 5.1 answer key. And so what I want you to do is I want you to go through and finish this frequency table, and then you can use this frequency table and a graphics calculator, call X bar list 1, the frequencies list 2, so list 1, list 2, and then you can do one variable statistics to get the mean and standard deviation. Now this is called a frequency distribution. That was actually on our first test. You just have to gather all the information from here. Now notice how lucky we were. I didn't make you find all 64 of those. So that was quite a chore. And so fortunately they had a picture in the back of the book and we could use it. But that's what we need to do everything we need to do. So if everything worked out properly, then what you were able to figure out is that the mean of the sampling distribution, and this is the notation for that, is 3.5, and that the standard deviation of the sampling distribution as sample means is 1.71. And what we are supposed to do is we're supposed to compare those to the mean of the population, which is 3.5, and the standard deviation of the population, which was 2.96. And so what I want you to do is I want you to think about what that comparison is, and you might want to look at the central limit definition again before you do that. I didn't finish the frequency table. I'm assuming you did that. I also just told you how to find these values, and these were the values you found from your list 1, list 2, making the frequency table for this distribution over here. Okay? So let's work on our comparison. Pause the video, take a moment to think about it, look at the central limit theorem, and then we'll talk about comparison. And so the central limit theorem tells us that if we have a population, and our population was 0, 2, 4, 8, the number of movies watched by a family member in 1 month. And we create a sampling distribution, and our samples were of size 3, and so we'll call S our sampling distribution. And that consisted of all these little 3 set things, 64 of them in our sampling distribution. So if you have a population and a sampling distribution of all samples of the same size, then the central limit theorem says that the distribution is a normal distribution. Well, one of the ways you can check to see if it's normal is you could take your frequency table and you could draw a histogram from that frequency table. Okay? And so for 0, you had 1, right, at 0, and then at 0.67, you had, it was 3 high, and you could go ahead and draw a histogram for that. And what you will see is your histogram is going to have this kind of symmetric bell curve shape that we've all come to expect. The next thing, and so that's how you could show that it was approximately normal. The next thing the central limit theorem says is that the mean of the sampling distribution is exactly the same as the mean of the population. And what we see here is that our means are equal, aren't they? They're both 3.5. So that's the first thing we would have noticed. And the central limit theorem said that had to be so. The second thing the central limit theorem says is that the standard deviation of the sampling distribution is equal to the standard deviation divided by the square root of the sample size. And so our standard deviation was 2.96. And if we divide that by the square root of 3, we should get 1.71. So 2.96 divided by square root 3, and we get exactly 1.7, not exactly, but approximately 1.71. So what that tells me is that this sampling distribution shows me that the central limit theorem is true if you can get all samples of the same size. So that's a pretty good deal, and that's a pretty good strong theorem. So your job for tomorrow is to do problem 10. Problem 10 requires you to, with this data or some data, make samples only of size 2. So your sample space is only going to have 16 elements in it, and you're going to do it with replacement. When you're done, you're going to create a frequency distribution. You could make a frequency histogram out of that. You're going to then use a graphics calculator to find the mean and the standard deviation. Now, if you get everything done up to the distribution, you can do that right when you get to class at the start. So what I'm expecting to see is really some progress towards getting these two numbers right here using a graphics calculator. So I'm going to need to see this histogram, which will show me that you're working through the process. Okay? So that's what you need for tomorrow. All right, that's it for the video.